Hello and welcome. This is Unit 2 for GCSE Chemistry for AQA. This is for both Combined Science and Triple Science students. The Triple Science content is labelled in the video, as is any higher content that is needed. Timestamps in the description below. Other than that, let's get going. We're going to first look at bonding and ionic bonding. So in terms of bonding overall, we have chemical bonds. These are bonds between atoms in an element or a compound. There are three strong chemical bonds that we need to know about. They are ionic, covalent, and metallic. In terms of ionic bonding, this happens between metal and non-metal atoms. It involves the transfer of electrons, and it's caused by oppositely charged ions. We'll take a look at that in more detail in a moment. Covalent bonding, this is between non-metal and non-metal atoms. This involves the sharing of pairs of electrons. Atoms can be of the same element, for example in oxygen, or the atoms can be of different elements, for example carbon dioxide. For metallic bonding, this is in metal elements and in alloys. This involves sharing delocalized electrons, and it's between the atoms in a metal. Let's take a look at ionic bonding in a bit more detail. In ionic bonding, electrons are transferred from the metal atom. The metal atoms lose electrons and become positively charged ions. The non-metal atoms gain electrons and become negatively charged ions. Let's take a look at bonding in sodium chloride. We can start by looking at the sodium atom, and we've looked at drawing atoms in the previous video if you want to go back and take a look at that. However, with sodium, we have a total of 2 electrons in the first shell, 8 in the second shell, and 1 electron in the third and outermost shell. The electron structure or the electron configuration is 2-8-1. We have 11 protons in sodium, and we also have 11 electrons. This means the atom is going to be neutral because the protons are positive and the electrons are negative, an equal number of both, so they balance each other out. For chlorine, we have 17 protons, so therefore 17 electrons. And in our first shell of chlorine, we have 2 electrons. We have 8 in the second shell. And in the third and outermost shell, we have 7 electrons. That makes a total of 17. The electron configuration or electron structure is 2-8-7. 17 protons, 17 electrons, and again, because we have equal numbers of protons and electrons, the atom is neutral. Now, when we have a chemical reaction between sodium and chlorine, we have the transfer of an electron from the sodium to the chlorine. 1 electron is transferred, and the reason for this is so that both atoms gain a stable arrangement of electrons, in other words, a full outer shell. You can also say they gain a noble gas configuration, but mark schemes allow these 2 points for the mark. We get rid of the outer shell of our sodium, and we can see that the electron structure of the ion is 2-8. We have 11 protons, but now 10 electrons. This means that the atom gains a charge. For our chlorine, we have a new electron arrangement of 2-8-8. We don't have 17 electrons anymore, we have 18, and again the atom gains a charge. The sodium atom becomes a sodium ion, and we can draw it out like this. We draw square brackets around the ion. We have a little plus sign meaning +1. We don't usually write +1, we just usually write a plus. And for chlorine, this is no longer called chlorine, it is now a chloride ion. It has a full outer shell, it has a charge of -1. We just usually write a minus sign when it's just a single minus or a single plus. Now, because the sodium ion has a positive charge and the chloride ion has a negative charge, those two will attract. We call this an electrostatic force of attraction. Now you may see these ions drawn slightly differently like this with just the outer shells drawn. This is perfectly acceptable. And again we have the electrostatic force of attraction between those two ions. Let's simplify the structure of those ions further so we can see the structure of the compound sodium chloride. So there's just 2 ions in the structure, but sodium chloride doesn't just have 2 ions in its structure, it has many. So that's it drawn out there for us. We need to be able to describe the structure of ionic compounds. Sodium chloride is one example, but this is the same for the ionic compounds that we study. Ionic compounds are giant lattice structures. The structures are held together by strong electrostatic forces of attraction between oppositely charged ions. Please remember that the forces of attraction act in all directions, up, down, left, right, backwards and forwards. We should also be able to talk about the properties of ionic compounds, and these are that ionic compounds have high melting and boiling points. The reason for this is because a lot of energy is needed to break apart the many strong bonds, the many strong ionic bonds that hold the ions together. They cannot conduct electricity when they are in solid form. This is because the ions are in fixed positions and are not free to move, and also there are no free electrons to move around either. However, they can conduct electricity when they are dissolved in water or when they are molten. Molten just means melted because of heat. The reason they can conduct electricity when dissolved or molten is because ions are free to move and so charge can flow. Let's take a look at covalent bonding. When atoms share pairs of electrons, they form covalent bonds. Covalent bonds are strong, and all molecules have covalent bonds. We associate the word molecule with covalent bonds, so therefore ionic structures do not have molecules. There are several covalent structures or covalent compounds and substances we need to know. Those are listed there. Also, please remember, electrons are shared, so atoms gain a stable arrangement of electrons. In other words, they form full outer shells. Let's take a look at these individually. We'll start with the substance chlorine gas, that has a formula of Cl2. We're going to draw just the outer shells for all the substances that we're going to look at for covalent bonding. Here are 2 atoms of chlorine side by side. We draw the electrons as dots and crosses so we can see the origin of the electrons as they bond. And when we have bonding in chlorine as a covalent bond, the 2 atoms join together and share 1 pair of electrons. You can see that each atom now has 8 electrons in the outermost shell. It has a full outer shell, or we could say a stable arrangement of electrons. And that's how it's achieved in covalent bonding. Another way you must recognize how to draw covalent bonding between atoms is like this. So it's pretty much the same, but just without the shells drawn. And we must recognize it like this with a single line between the chlorine atoms. This line represents a single covalent bond. That means 1 pair of shared electrons. We can see the covalent bond in both of our other diagrams as well. So there's chlorine. Let's take a look at something called hydrogen chloride. Here's an atom of hydrogen. Here's an atom of chlorine. And if you're thinking ahead a little bit, you can see that they would join by sharing that pair of electrons. A second way of drawing that is like this. And the single bond is drawn like this. Please remember, hydrogen only has 1 shell, so 2 electrons in its outermost shell means it's full. There's hydrogen chloride. Let's take a look at water. This involves 3 atoms altogether. So here is our oxygen with its 2, 4, 6 electrons in the outer shell. Here's hydrogen, and here's another hydrogen. And again, you can see the full outer shells are achieved like this. We can also draw a water molecule like this without the shells. And again, we can draw it in a third form as seen on the screen there. That's water. Oxygen is slightly trickier. So with oxygen, we can share a pair of electrons, but that would mean that both atoms do not have a full outer shell. So they don't have a full outer shell. So what we do is we share 2 pairs of electrons. You can see now that both atoms have 8 electrons in their outer shell, a full outer shell. Again, our double bond is shown like this in our second form of the diagram. And when we draw a double bond in our third form, it's drawn by 2 lines. So there's our double covalent bond. It's 2 pairs of shared electrons. And again, you can see in our other diagrams as shown by the arrows. So that's oxygen. Let's take a look at nitrogen, and again, slightly tricky. However, if we look carefully, we can't just share one pair of electrons. In this case, we actually have to share 3 pairs of electrons in order for both atoms to have a full outer shell. So this is how we draw nitrogen without the shells, and we show the triple bond like so. That's 3 pairs of shared electrons, as shown by the arrows on the other diagrams there. That's nitrogen, and again we go back to being slightly more simple now. So this is ammonia. Nitrogen has 5 electrons in the outer shell. We bond with 3 hydrogen atoms, and quite simply, this is how we achieve a full outer shell for all the atoms there. Again, second way of drawing our diagram, and the third way there. The final one is methane, again quite straightforward. The carbon atom with its 4 electrons in its outermost shell, 4 hydrogen atoms, all sharing electrons like so. And there's our 2 other versions of the diagram that we must know and recognize for our GCSE chemistry. We're going to take a look at the properties of substances made of small molecules. Substances made of small molecules have relatively low melting and boiling points. For example, oxygen melts at minus 219 degrees Celsius and it boils, turns to a gas, at minus 183 degrees Celsius. You don't need to memorize those numbers. This is just an example that I'm showing you. Here are the molecules of solid oxygen. So you can imagine this is below minus 219. However, if we apply a small amount of heat, those molecules will separate. Let's see what's going on. We apply a small amount of heat energy. The molecules separate. What you can see is that between the molecules there are weak intermolecular forces holding those molecules together. And this actually goes for all substances made of small molecules. So they all have low melting and boiling points because the intermolecular forces of attraction between the molecules are weak. So only a small amount of energy is needed to overcome these forces of attraction. Please remember, this goes for all substances made of small molecules. Those intermolecular forces increase with molecule size. This is methane. It has a boiling point of minus 162 degrees Celsius. You don't need to memorize that number. But if we look at ethane, a slightly larger molecule, or made of slightly larger molecules, its boiling point is higher. Minus 89 degrees Celsius is higher than minus 162 degrees Celsius. Ethane is made of larger molecules, so has stronger forces of attraction, which need more energy to break, so therefore the boiling point is higher. Intermolecular forces are weak, remember, and covalent bonds are strong. There's our intermolecular forces between molecules, and there's our covalent bonds, which are strong, not between molecules, but between the atoms in the molecules. Small molecules have no overall electric charge and no free electrons. That means the substance, for example oxygen, cannot conduct electricity. There's no free electrons to move around. So that's the key information about substances made of small molecules. We're going to take a look at polymers now. Polymers have very large molecules, and the bonds between atoms in polymers are covalent, which means they are strong. Intermolecular forces in polymers are relatively strong. These are 2 very large polymer molecules, and we have relatively strong intermolecular forces between the molecules. Remember, the covalent bonds between the atoms are strong. The relatively strong intermolecular forces make polymers solid at room temperature. That's pretty much what we need to know about polymers for this unit. Next, we need to look at giant covalent structures. These are solids with very high melting points. All the atoms are linked to each other by covalent bonds. I've just noticed I've written the word R twice. Let's fix that. There we go. The first structure we need to know about is diamond. Here is the structure of diamond. It's made of all carbon atoms, or only carbon atoms. And diamond is very hard. This is because it has a giant lattice structure, and each carbon atom forms 4 covalent bonds, which are strong, with 4 other carbon atoms. There are no free electrons, so diamonds cannot conduct electricity. The next one is graphite. This is the structure of graphite. Again, it's made of carbon atoms only, and each carbon this time forms 3 covalent bonds. This forms layers of hexagonal rings, and there are weak forces of attraction between the layers. There's the weak force of attraction labeled there. Because these forces of attraction between the layers are weak, this allows the layers to slide over each other very easily. This makes graphite soft and slippery. Please note also there are free, or what we call delocalized, electrons in graphite. The third and final giant covalent structure we need to know about is called silicon dioxide, otherwise known as silica. Here is the structure of silica. Silicon dioxide is hard. This is because it has a giant lattice structure, and each silicon atom is covalently bonded to 2 oxygen atoms. There's 2 silicon atoms in blue, and the oxygen atoms are in that grey colour. There are also no free electrons for silicon dioxide. That means silicon dioxide cannot conduct electricity. So those are the 3 giant covalent structures we need to know about. I just want to add one more bit of information about those. We said diamond does not conduct electricity because there are no free electrons. Graphite can conduct electricity because there are free, or what we call delocalized, electrons that can flow through the structure and carry charge. Silicon dioxide does not conduct electricity because there are no free electrons, very similar to diamond, but also all 3 have high melting and boiling points because the atoms are joined by covalent bonds which are strong and require a lot of energy to break. Let's move on to the next part. This is metallic bonding and the fullerenes. Let's start with the structure and properties of metals and alloys. Here is an example of some metal, e.g. copper wire. If we were to focus in or zoom in, if we were able to, you would see that the atoms in copper, like any other metal, are arranged in a lattice structure. This is another way of drawing the atoms in metals. The structure and bonding in metals. Metals are giant structures of atoms, or we could say ions. The electrons in the outer shell are delocalized, so are free to move. There's our delocalized atom shown by the cream kind of color in the first diagram, and as shown as electrons in the second diagram. This sea of delocalized electrons holds the metal ions together and makes strong metallic bonds. Metals can conduct electricity. This is because the delocalized electrons can carry charge and flow through the metal. So let's take a look at that. Here's an example of a few electrons. These can flow through the metal, through the structure, carry charge, and therefore the metal can conduct electricity. Metals are also good conductors of heat energy because energy is transferred by those delocalized electrons. In pure metals, the atoms are arranged in layers which can slide over each other. This means metals can be bent and shaped. Here again is the diagram. Metals can be bent and hammered into shape because the layers can slide. In terms of alloys, you can see the structure is slightly different. Alloys are harder than pure metals. This is because alloys are mixtures of metals, or mixtures of a metal with non-metal atoms, and the layers are distorted by the other atoms, so the layers don't slide over each other very easily at all. This makes alloys harder than pure metals. So that's key information about metals. Let's take a look at graphene and the fullerenes. Graphene is a single layer of graphite. It looks a bit like this. If you're looking from the top, you might see something like this, and here's what's supposed to be a kind of 3D version of that diagram. Again, each carbon atom is covalently bonded to 3 others to make a layer of hexagonal rings. Free electrons can flow and carry charge through the structure, so graphene can conduct electricity. Graphene also has a high melting point because a lot of energy is needed to break the covalent bonds. So that's graphene. Let's take a look at the fullerenes. The first fullerene ever discovered was called buckminsterfullerene with the formula of C60. It looks like this. It's made of carbon atoms. C60 is a spherical or ball-shaped molecule. The carbon atoms are in hexagon and pentagon shape, so you can see that as outlined in red, one hexagon and one pentagon. Each carbon atom is bonded to 3 others. There are free electrons that can move over the surface, but not between the molecules, so C60, buckminsterfullerene, is a poor electrical conductor. However, one feature that it has is that it's a good lubricant because the molecules can roll. Let's take a look at nanotubes. These also contain hexagonal rings, but this time in a cylindrical tube shape. Nanotubes have very high length to diameter ratios, in other words they are long and thin. Each carbon is bonded to 3 others, and nanotubes can conduct electricity because there are delocalized electrons that can flow and carry charge through the structure. Nanotubes and the fullerenes are useful for nanotechnology, electronics and materials. By electronics we mean circuits in computers or wiring in aircraft. It would make the aircraft much lighter, burning less fuel, therefore contributing less to the greenhouse effect. And for materials we're talking about things like tennis rackets, which become light and strong, and the same for bike frames. Potential uses for graphene and nanotubes are based on strength and high melting points because of the covalent bonds between the carbon atoms. Also the ability to conduct electricity because of the delocalized electrons that can flow and carry charge through the structure. Potential uses for buckminsterfullerene is based on the idea that it has a hollow shape, and it's got potential uses for delivery of drugs in the body, medicinal drugs to cells in the body, and based on its spherical shape because it makes it good as a lubricant to reduce friction between moving parts. We now move on to the 3 states of matter: solid, liquid, gas. In solids, the particles are close together in rows and columns. They vibrate in fixed positions. In liquids, the particles are in less of a regular arrangement and they are free to move around. In gases, the particles are far apart, moving in random directions and at different speeds. To go from solid to liquid, that's called melting, and liquid to gas, that's called boiling. From gas to liquid, that's called condensing, and liquid to solid, that's called freezing. Please note that the point at which a substance melts and freezes is called its melting point, and the point or the temperature at which it boils and condenses is called its boiling point. Remember, particles gain energy when the substance is heated and lose energy when the substance is cooled. Also important to remember is that particles themselves do not melt or boil. For example, we can say that water boils. This is correct, but we cannot say that water molecules boil because that's technically not correct. So we wouldn't phrase it or say it like that. Remember, the stronger the forces between the particles in a substance, the higher the melting and boiling points. We studied this a bit in our Unit 1 video. Here's the example of the halogens. Fluorine would be at the bottom there. Then we have chlorine. Then we have bromine, and then we have iodine. You might want to take a moment just to pause there and just check out those temperatures and make sure you can see why they're in that order there. And we need to be able to decide on the state of these at room temperature. Room temperature, we will say, is 20 degrees C. So it's worth, again, having a pause and see if you can work that out. But if not, iodine is a solid at room temperature. Bromine is a liquid because it would have melted at -7 but not yet boiled at 58 degrees Celsius. Chlorine would be a gas, and fluorine would be a gas as well. This next bit is for the higher tier. The limitations of using models as we are doing here to show bonding and changes of state. Let's compare the model with reality, the model being either diagrams or actual physical models. In the model, the particles are shown as solid spheres, whereas in reality, the particles are atoms, molecules, or ions, and they are almost all empty space. In a model, the particles don't show the forces between them, or they show the forces as lines. In reality, the particles have forces between them or are bonded together. Particles are not usually shown as bonded in the model, but different bonds do exist between the particles, for example, ionic, covalent, or metallic. Particles are not moving in our model, or not often moving in our model, but in reality the particles are either moving or vibrate about fixed positions as they do in solids. Next, let's take a look at nanoparticles. This is for triple science students only. If you are not a triple science student, you are good to go. So, triple science content only, we're going to take a look at the bulk and surface properties of matter, including nanoparticles. Nanoscience refers to structures that are 1 to 100 nanometers in size. Nanoparticles are only a few hundred atoms in size. If you are asked about the size of nanoparticles in an exam, you could say that they are 1 to 100 nanometers in size, or you could say they are only a few hundred atoms in size. Both of those would score a mark. So nanoparticles are 1 to 100 nanometers, that's 1 times 10 to the minus 9 meters. And something called fine particles, that's PM 2.5, just shown in standard form there, are 1 times 10 to the minus 7 to 2.5 times 10 to the minus 6 meters. Coarse particles, PM10, are 2.5 times 10 to the minus 6 to 1 times 10 to the minus 5 meters. All these measurements are measured in the specification, so it might be safe just to make sure we have memorized those. Coarse particles, remember, are often called dust. Surface area to volume ratio. This is quite important to know about when we're talking about the properties and applications of substances with nanoparticles. As the side of a cube decreases by a factor of 10, in other words 10 times smaller, the surface area to volume ratio increases by a factor of 10. That's 10 times bigger. So let's have a look. Our first column is length of cube side, then we're going to look at the surface area, then we're going to look at the volume, and then we're going to look at the surface area to volume ratio. So for the first one, we have a cube side of 10 millimeters. That would give a surface area of 600, because it would be 10 times 10 for one surface times 6 for all the surfaces on a cube. That would give 600. And the volume is given by 10 times 10 times 10, which is 1000. If we divide the surface area by the volume, that gives the surface area to volume ratio. That's 0.6. If we make the length of the cube side 10 times smaller, the surface area is now 6. The volume is now 1. This is a bigger surface area to volume ratio. Again, if we decrease by times 10, we have a surface area to volume ratio which is much bigger. And if we go smaller still, the length of the cube side as 0.001 millimeters, the surface area is that, the volume is that, and the surface area to volume ratio is a massive 6000. So you can see the smaller the size of our particles, the bigger the surface area to volume ratio. If we were to look at it in a graph, it would look a bit like this. And if we look at the size of particles in the smaller region of the graph there, you can see that the smaller you get, the bigger the surface area to volume ratio. Uses of nanoparticles. These are used in cosmetics and sun creams, in deodorants, in electronics, in medicine, and as catalysts. The effectiveness is often to do with the very large surface area to volume ratio of nanoparticles. This means smaller quantities may be needed than for materials with normal sized particles. For example, sun creams with UV absorbing nanoparticles. You can use a smaller amount of sun cream and absorb more UV light. Silver nanoparticles can kill bacteria. For example, they can be used in socks to help keep them deodorized. And a small mass of catalyst can be used for chemical reactions, which will have a big effect because of the big surface area to volume ratio. There are risks to using nanoparticles, potential risks. They might be able to get into the body cells and cause damage. We don't know the long-term effects because they have not been used over the long term, and because of their size, potentially they could get into cells and into the cells of animals and living things in, for example, waterways. That's it for the video today, Unit 2 for AQA GCSE Chemistry Combined and Triple Scientists. Thank you for watching, and I'll see you soon.